Hi. So I want to go back to this problem that I initially posed as the reason why we need to study the solution of the Laplace equation in the cylindrical coordinates. So we seem now to have the necessary mathematical background. So let's try and see if we can attack this problem with any success now. Um, okay. So the first choice that we have to make is whether we need to choose the Bessel function or the modified Bessel function. And it's originating from the issue of whether we choose the k-square or the minus k-square as the coefficients to be used in the separation of variables method. And I think it doesn't really matter. In the end, you will still obtain the same correct solution. Um, but so I guess I'm just go with one choice of the sign and see what happens, and probably leave the other choice of the sign as something for you to figure out on your own. So I'm gonna go with this modified Bessel choice. In that case, the full solution is given as the superposition of this type of functions, where the radial dependence is given by the modified Bessel function, and the z dependence is given by the oscillatory function. And we're going to use the property of the Bessel, modified Bessel, that the at the zeroth order, this function has the symmetry, which makes this an even function of its argument. So by composed of, what I mean exactly is that the full solution is a superposition of these functions with some coefficients that depends on the k wave number, and that's this a of k thing. And then naturally we move on to the next question of determining what this a of k is. But you see, these cylinders are infinite in our problem. So it goes off to positive infinity in this direction and goes off to negative infinity in the other direction. So in this circumstance, there's no boundary condition to be imposed, because usually boundary condition comes from imposing some sort of restrictions at the end, but there's no end here. And therefore, we're not going to be able to quantize the k as we did in many of the previous problems. And as a result, the sum becomes the integral. The Fourier sum becomes the Fourier integral. And I do sincerely hope that you are already familiar with this procedure of going from the sum to the integral when the wave number is allowed to change continuously. And I have to skip the small necessary mathematical intermediate steps and just jump to the conclusion to say that this is what you get from writing the solution, writing the potential as a Fourier integral. Okay, so instead of sum over the k, we have an integral over k going from minus infinity to plus infinity. And still the task is to figure out what this coefficient function a of k is. So we're going to bunch these product of two functions as some single function b of k, and then phrase the problem as that of finding the b of k. And this is, of course, found by performing the inverse Fourier integral of this expression. So when you do the inverse Fourier, then this is what you get. Okay, so far, I tried to make it natural what I did, but actually you'll find that there's something slightly funny going on here because we do have the dependence on the radial coordinate rho here on the right hand side of the equation, but on the left hand side we have nothing. So at first it seems pretty confusing. And also over here we have this rho dependence through the argument of the modified Bessel function over here. So therefore, there's rho dependence in the potential on the left hand side, but I pretended as if there's no rho dependence in this product. Okay, so you may be a little bit confused by this, but I think what really is happening is that this result is independent of where you evaluate this Fourier integral. You can choose rho as rho equal to 0, or you can choose rho equal to r, the radius of the cylinder. You can choose rho to be any value you want, and still you will find exactly the same answer once you perform the Fourier integral. So it's not wrong. This expression is not wrong. It's only telling you that you have this interesting freedom in choosing the rho value. And of course, you have to choose it in a way that will make the computation most convenient. And that's what you do once you have this kind of freedom in the calculation. Well, obviously, then we have to choose this rho to be the circumference of the cylinder. The radius of the cylinder, because that's where we know the value of the potential exactly. So on this side, where z is less than 0, you have the potential on the surface of the cylinder equal to V1. And on this side of the cylinder, you have the potential equal to V2. All right, so then we will take advantage of that knowledge and say that if we choose rho to be the radius of the cylinder, then for this side, the negative side, this potential function reduces to a constant V1. And on the positive side, this potential reduces to another constant V2. All right, so then this integral is really simple. This is probably the simplest integral you can imagine performing, and that's the result. This is the overall result of the integral. Okay, just one minor note. When you do the integral and arrive at this result, there's a small trick that I had to play. And I really want you to figure out what is that trick that I played. Okay, that's another piece of homework problem that accompanies this lecture. And the answer is actually already in the textbook as a footnote. So just look it up and digest that. Okay, so now I think we got what we want. We wanted to know what this coefficient A of k looks like, and this relation will allow us to obtain this A of k in a nice closed form, and therefore we are able to express the potential as the Fourier integral of some sort. Okay, so there's a bunch of functions to be integrated over. There's a modified Bessel, and there's a plane wave, and there's a 1 over k. So it's a lot of functions all strung together to digest and also to integrate over. But now you can see there can be some simplifications. Namely, if you note that this exponential breaks down as the sum of the cosine and the sine, and only the sine part will survive the integration because of symmetry. The cosine part is even, but this 1 over k thing is odd, so therefore the integral over the entire range of an odd function you expect to be 0. So only this part will contribute to the integral, and therefore the final expression will simplify actually to something that looks like this. And you can always add a arbitrary constant without changing the physics. And this constant is to be chosen in such a way as to satisfy the boundary conditions of the problem. Okay, so now, so this is the most simplified version of the integral that one needs to perform, and the considering taking into account the boundary conditions, you can realize that this constant term has to be this. So that's the average potential between the left half of the cylinder and the right half, and that's completely reasonable. And this other piece, which depends on the potential difference, then has a natural interpretation as something that captures the effect of the disturbance. So by disturbance, what I mean is that you have to make a transition from the region where the potential is more or less V2 to the region where the potential is more or less V1. So there will have to be a transition region. And what exactly is going on in that transition region is captured exactly by this integral. And I realized that this integral is actually very easy to analyze in the limit where rho goes to 0. That's along the axis of the cylinder. So along that axis, we have this integral form. And you see that this z dependence comes through this step function. Okay, so the overall result of the integral is this potential difference multiplied by the step function, and on the graph it will look like that. So that's exactly what we expect as the transition behavior. On one side you have the potential, which looks more or less like the V1. On the other side you have the potential looking more or less like V2. So from this quite simple exercise, you can see that this integral really captures the transition behavior rather well. Okay, so there's a couple of unresolved issues, like what's the shape of this potential when rho is not equal to 0, but some finite value. And the other question is, what if we use the Bessel instead of modified Bessel? Then we will still obtain the same behavior, same function for the potential. I'll leave those questions as a free exercise for you guys for your intellectual enjoyment. Thank you.